why they study this, I guess, is I think it's definitely very interesting to study what are the possible second eigenvalues in this range, right? So we already know that the second eigenvalue of the regular graph has to be here. The first eigenvalue is not interesting, it's always D. The second eigenvalue has to be here, but what are the possible second eigenvalues? It cannot be everything, right? Because the second eigenvalue we know are the solution to characteristic polynomial, which are, say, polynomials with integer coefficients. So your second eigenvalue has to be some, I guess, algebraic integer, algebraic number. So it cannot be, say, pi or any other transcendental number. But can any algebraic integer in this interval be achieved as a second eigenvalue? I don't think people know that. So people still don't know what are the possible second eigenvalues within this interval. When they don't know that, they might study how is it possible that these second eigenvalues can be as close to anything in this interval. So that's my guess of a motivation to study this result. Okay, good. So the result I'm gonna present today by Theo and I is a generalization of this result. So before stating our result, I will first state a generalization of Alon and Wei. So here we know that the second eigenvalue of the regular graph is asymptotically at least 2 root d minus 1. But actually, we are able to replace this 2 by any constant. And the result still holds if we send n to infinity. So for any k, say, fixed constant k. As n goes to infinity. The kth largest eigenvalue of G is asymptotically at least 2 root d minus. So the same lower bound. Okay, and so therefore we know that when the vertex number goes to infinity, any finite number of top eigenvalues must lie in this range. And then we can naturally ask, can these finite numbers converge to any tuples within this simultaneously? And that will be our result. So if we can write this formally, it will be for every A1 through AK, where A1 is D. For every A1 through AK between D and 2D minus 1 and A1 equals D, there exists a sequence of D regular graphs. G1 and G2, such that each of the ith eigenvector converge to AI. So this is our result, and hopefully it's clear that it's generalization of Alon and Wei result. Do people have questions so far?
Can you tell me who proved this generalized Alon, or is it directly?
It's definitely more than one groups of authors. So one author is by Sarah, and another author is Okay, if that's helpful.
We need,
Yes, yes, yes. Yes. And probably even more authors other than these two. But they all prove this, I think, independently. Yeah. So sorry, I should add authors to here. But there are many groups, so maybe I was being lazy, which I shouldn't. Okay, do we have other questions?
So the proof is by construction, you construct that, like.
Yeah, yes. So we can already see from the statement here that this proof is by construction. So for every tuple, we want to find a sequence of graphs that achieve this. Do we have more questions? Okay, great.
So we're saying for all k, there exist direct graphs with that, or
Are you looking at this?
Yeah, the last
result
one,
or
yes.
this result?
no, this.
This result. Yes. So let's say k is like 100, and and let me take an infinite sequence of say 3 regular graphs or something. What we know is that when say when j goes to infinity, lambda 100 j will be asymptotically at least we will say asymptotically at least 2 times like 3 minus. Is this clear here? So basically, if I have a sequence of d regular graphs, I look at the associated sequence of kth largest eigenvalue, then I know that they have the infimum at least 2d minus 1. Okay. Okay, yeah, okay, so now I will talk about the proof strategy of our theorem. So I don't know how people familiar with the spectral graph theory, but hopefully what I prepared will be understandable enough to people, to everyone who know more or less. So as you correctly said, this is a proof by construction. So proof. So first idea. So again, like I want a irregular graph, G, whose first eigenvalue is like D, second eigenvalue is like arbitrarily close to A2, and up to kth eigenvalue is close to AK. Right. So this seems very hard because I need to simultaneously control k different eigenvalues. So the first step will be to reduce this to breaking G into subparts, so that for every subpart, I only need to control one eigenvalue. So it would be nice to break G into subparts. So that for every part, we only need to control one eigenvalue or 2. Okay, so this idea was developed by the previous authors, Alon and Wei. They developed this patching lemma.
Excuse me,
Sorry.
my question, so like the eigenvector associated with lambda 1 should be like all one's vector.
Exactly.
But that depends on like the whole, like somehow every vertex matters, but for the other k minus 1 eigenvalues, we want to somehow only look at certain pieces of the graph for each eigenvalue. Okay. I guess I'm a little surprised because like somehow the first eigenvalue you require, like because the eigenvector is all ones, you sort of need to know everything. Like it looks at the whole graph.
Yeah.
But for these other eigenvalues, you only have to look at parts of the graph. So
yeah, no, I think I understand you. So you're saying in our G, the first eigenvector is all one's eigenvector.
Yeah.
But from the second to the kth, it's like only supported.
Yeah, somehow, yeah.
So first of all, that is true.
Yeah.
That might be surprising, or is there a?
But I
good
guess this is
explanation?
not in general, it's you construct one which has this kind of structure, yes. For general G, maybe you still need to look at the whole thing. I don't know.
You don't want to say random one. Random one doesn't satisfy this.
Sure.
You want to have an atypical graph.
Okay.
Actually, I have a different question. Is the smallest one also interesting, or it's
The smallest one is interesting, and I think Alon and Wei prove something for the smallest eigenvalue. I forgot the result,
okay?
but our paper doesn't contain anything about the smallest eigenvalue.
So here the break means like blocks of G.
We will elaborate what we are doing here. Okay. So yeah, no, let's look at the patching. So this idea was like developed by Alon and Wei. So they phrase this as a patching lemma. So I will maybe slightly rephrase it, which will look like the following. So suppose G1 up to say G, I'll do K minus 1 are say sufficiently long tree extensions. We will explain this in a second. And G0 is a sufficiently large D-regular graph with a sufficiently large girth. And suppose, let's say the first eigenvalue of G1 is say A2. Yeah, I guess we have to do this. Okay, suppose G2 through GK. So the first eigenvalue of G2 is A2, which for now, let's say bigger than 2 root D minus 1. And D, and similarly for all GK. Okay, then there is a way to glue G2 through GK. Okay, maybe I want this to be G1. Yeah, that doesn't really matter. Yeah, there is a way to glue G2 through GK onto G1 such that you know, the first called the glued graph H. Okay, everything so far is super unclear, but we will elaborate on this. Call this glued graph H. Such that the first K eigenvalues of H are, you know, approximately. Okay, so sorry, I need to add the second eigenvalue of G2. The second eigenvalue of all of these let's say, you know, smaller than 2 root D minus 1 plus delta, where delta is a very, very small constant that's, okay, you know, let's say much smaller than say, or whatever, okay. Okay, then there's a way to glue these G2 through GK onto G1, so that the first K eigenvalue of this glued graph H as asymptotically, is approximately equal to the first K eigenvalues of, the disjoint union of G1 through GK. Which are lambda, which are D, A2 to A. Okay, so what is this doing? So first of all, what is a tree extension? So tree extension of say depth L. So definition, let F be a graph with maximum degree at most D. The tree extension of depth L of F, which we denote by TL of F. So this is obtained by attaching some number of level L D regular rooted trees to every vertex of F, so that the obtained new graph is deregular on F. So attaching D minus degree of V rooted D minus binary tree.
But the leaf has degree 1.
Leaf has degree 1, yes.
So except those leaves, you have degree D.
Exactly.
Okay.
Yes. To every vertex of V of F. Okay, let's try to draw a picture so that we understand. So let's say D is 3. F is maybe this. Let's say if we can draw this. And then L is 2. Okay, so what is T2 of F? So I start here. These have like degree 1, 2, 2, 1, but I want to complement, add trees to it so that everything here becomes 3 regular. So I want to add 1 tree here. And then I need to add, say, 2, level 2 trees. And then I will do the same here. And here I have degree 1, so I need to attach 2 trees to it, so that this becomes degree 3. And this is my tree.
That view L is 2 or 3.
L is 2.
This is why it's 2. It looks like
You range
I mean,
twice.
So eventually it's not very important, but let's say this is my root. This is level 1, this is level 2. So this is my root. These are roots.
Okay.
Yeah. It will not matter in the end, but
Okay.
but this is a tree extension. So this is what we call a tree extension. Okay, by sufficiently long tree extensions here, we mean that they are TL of F for some F, whatever that F is, we don't care, and sufficiently large L. Okay, so in our head, G2 through GK should look something like this. like in our head, G2 through GK should look like this, where these are just like a very, very long trees, and these are my original Fs. Okay, so now the claim is that we can glue all of these onto G1, where G1 is a now super large deregular graph. It needs to be very large because we extend each of these for many times. So the number of leaves here are like, you know, d minus 1 to the L times the original vertex numbers. So very, very large. And so G1 need to be much larger than all the leaves here. Okay, so
What's that word? Sufficiently large?
girth, yes. So girth is like length of the smallest cycle. So if I have girth 10, it means my graph doesn't have a triangle 4 cycle, 5 cycle up to.
But D already has a G1, sorry. G1 already has degree D. And then if you attach to it something, then the degree will be larger than D.
That's a very good question. So this graph doesn't seem deregular, right? G1 is already deregular. If I add these trees to it, how can it still be deregular? So what we actually do is, so I have each of these leaves, right? So so I will find a bunch of points in my G1. And for every point, I will remove this point so that all these neighbors of it now become degree D minus 1.
Ah.
Right, so I throw away this point so that all these neighbors have degree D minus 1.
Okay, so then the leaf
The
attached
leaf
to
has
all
degree
of
1.
them.
Right,
Okay.
and now I just identify these two so that this will become degree D again. And if we stare at this tree extension, we see that everything other than the leaves have degree D. So, okay, so now this way of gluing will make the whole thing degree D again. Okay,
But
so
effectively, you already planned some long cycles because of those leaves. You can go between leaves from the G2 to GK.
yes. So there's some long cycle here. Yeah. There might also be some cycles within there, but we will see. Do we have other questions?
How do you make so the gluing will take leaves corresponding to some tree and like if I look at the last layer of this tree extension, there's like D minus there's D minus 1 many leaves. You attach them all together with another vertex?
Each leaf. Okay, so let's see. So okay, so let's say this is my TL of F, and I have these leaves. And on the other hand, I have these, you know, sorry. So actually, no, this is not a good picture. So yes, this is a good picture. Is this a good picture? Okay, no, this is a good picture. Sorry. Yes. Okay. Yes. Yeah. So this is my G minus some vertices. Right. So each of these points will have a degree D minus 1. Each of these points will have degree 1. Now I just say this. I overlay these two vertices. So now these two become the same.
Merge them together as one.
I merge them as one vertex. So now there's one neighbor going there. There's D minus 1 neighbor going there. I merge these two, so this becomes D.
Okay.
Yeah, so this is the gluing step. Okay, great.
So it's kind of intuitive, it's kind of, the larger matrix, essentially it's disconnected, that the connection is very, very weak, yes.
Exactly. Essentially, what happens is I have these things that are very far away from each other, and in between them, there are very, very long trees. But because these trees are so long, this will make the top eigenvector of these disjoint in support. Yes, that's morally what's happening. Great. Okay, so we talk about gluing, we talk about tree extension. So we probably need to explain what this is doing a little bit. So suppose we want these conditions. So why we want these conditions? Okay, so
Another question.
uh-huh.
I can understand in this way you will have the A2 to AK. How do you guarantee the original G1? Because that one, original, the G1 has the lambda 2, yes.
Yes, sorry, you're right. I need to add one condition of G1 also, which is lambda 2 of G1
also
is
small.
It's very small, yes. Also maybe this.
Okay.
Yeah, thanks. This is very important. We need to make sure the lambda 2 of G1 and all of these are very small, much smaller than the target eigenvalues. Okay, so good. So we talk about all of these. So why do we want these conditions? So okay, so suppose, okay, maybe let's first look at the disjoint union. So I have disjoint union of, a G1, disjoint union. GK. And I know that lambda 1 is like A1 through AK. I know that lambda 2 is, B1 through BK or whatever. Okay, so the question is, what's lambda 1, lambda K of the whole thing? Okay, so we want so I want the first K eigenvalues of the disjoint union to be A1 through AK, right? But let's say B1 is bigger than A2, then we don't know. So what we want is if the maximum of all these B1, or I guess if all BI is at most all AJ, all AI, then the first K eigenvalues of will be A1 3. This is like a pure, I don't even know, elementary school, like finding the K largest number among all of these. I want them to be these because all of these are smaller than all of the above. Nothing is happening there. Okay. So therefore, okay. So going back to here, then the condition that we desire here will be because we want A1 through AK to be any number here, right? So A1 through AK, we want them to be any number here. Therefore, I want the condition that for these A1 through AK as close to 2 root D minus 1 as possible, I can still make sure the lambda 2 of these GIs is small enough so that they don't interfere with the AIs. So technically, this means that we basically just want all these lambda 2 GI to be, say, asymptotically at most 2 root D minus 1. Yeah, we basically want this. So that we can prove this for AK as close to this as possible. So we basically want this. Good. So after all of this, we can reduce the original problem to the following theorem.
Wait over here. So lambda 2 is less than plus delta or minus delta? It's a plus delta.
Over there, I wrote plus delta, but let's say,
The plus delta, then it
but-
could be larger than 2 square root of d minus 1. Yeah.
but let's say delta is smaller than, say, ak minus 2 root d minus 1 or something. Yeah, I'm adding a plus delta there because if we show, if we do this, we might not always find.
Okay.
Because of the Alon and Wei.
Yeah. So we
Oh,
only know
I
that
see.
lambda 2 is at most 2
I see,
root
I
d
see,
minus
I see.
1
Okay.
plus a small number.
I see.
Okay. Okay, so after all of this, we will reduce original theorem to the following. Theorem for any a that's say between 2 root d minus 1 and d. There exists a graph f such that for all L sufficiently large, TLF is the first eigenvalue of TLF is like a plus minus epsilon. We can put epsilon. And the second eigenvalue of TL of F is asymptotic, is at most 2 root d minus 1 plus d minus 1. Sorry, plus epsilon. Okay, so we will show this, and the procedure to go from here to there is, so given all of these numbers for each a from A2 to AK, I find such a tree extension. Then I use the procedure over there to glue these tree extensions together. Okay, so okay, good. So how do we find such a tree extension? So this is like the main part of the paper, and I will write down how we find such F. So the procedure to find F is actually quite simple. So the first step is to take a random deregulate graph. Say H on n vertices. And then I will take a random subgraph. Maybe let's call this H0. A random subgraph H of H0 by including each edge with the probability P, where P is a function of A. And let me actually write down what is P. So P is chosen such that P times D minus 1 plus 1 over P equals A. Okay, so finally, I will let G be the tree extension of A. Of H, sorry. I guess this H is our F over there. Maybe I'll do F. Okay. yeah, so that's it. Okay, so maybe some heuristic, why are we doing this? So heuristic of why this works. Okay, so when I want A to be D, so which means I want my first eigenvalue to be D. Then I don't need to remove anything, right? So I will just take a random D-regular graph. If I don't, okay, so first of all, what is the tree extension of D-regular graph? It's like itself, right? So I have a D-regular graph. I complement all the vertices by trees so that they have degree D. But my original D-regular graph already have degree D, so I don't need to add anything. So the tree extension of a D-regular graph is itself. So therefore, when A equals D, this means I have F equals H, right? So I just take TL of H. So I don't need to include, sorry, I will include every edge. So P is 1. Okay, so on the other hand, when A is 2 root D minus 1. So now we will realize that the infinite D regular tree has like all eigen values at most D root 2 root D minus 1. So then I can just delete everything from my D-regular graph H. So F is like empty. P is 0. Okay, so the hope is that when A is like some number between D and 2 root D minus 1, I will just take a random subgraph of H so that and do this tree extensions, that the obtained thing is some average between the random D-regular graph and the infinite D-regular tree. And then furthermore, I know that lambda 2 of H is like asymptotically at most 2 root D minus 1. And this is, say, by Friedman's theorem. Yeah, Friedman's theorem show that the second eigenvalue of random D-regular graph is at most asymptotically at most 2 D minus 1. And so therefore we know that in both the random irregular graph and the infinite tree, the second eigenvalue is always at most 2 D minus 1, and therefore we expect the average to have this property. Okay, so this will be the construction of our tree extension. Like this. And now the remaining job will be to show that these two properties are both true. So the plan for the remaining of today is to show this. It's not to show this, but to introduce how roughly the idea how to show this.
Can you do that in 5 minutes?
So we have 50 minutes. Okay, so let me stop here and thanks for coming.
So this gluing construction, I guess, like you can get rid of one vertex from G1 because it's deregular, and then attach the leaves from, or at least one set of leaves from one of the trees to its neighbors. But like, I mean, it's not like the G can be decomposed into like, in other words, it's not like I can find n over d vertices in G1 such that if I delete them, every vertex in G1 has degree D minus 1.
You
So
need a very
That's a
big
very-
G, right?
That's a very good question. So you are saying how to let these vertices be far enough.
yeah, basically like because I can see how to do this process for a single vertex, but as I like delete more edges to allow connections, it should be harder and harder to do this. Yeah.
Yeah. So I think one nice thing about this problem is that there's no restriction on the vertex number of these.
I see.
So when we read the statement, nowhere says the vertex number is the same and that cannot be true.
It
So
should go to infinity.
it has to go to infinity. Yes. So we are allowed to pick our GIs to be as many vertices as possible. So the hope is that when G1 is really, really large, much larger than all of these, we can pick these points to be far enough from each other.
So I'm teaching Markov chain this semester.
Uh-huh.
So when I look at this matrix divided by T, it's very much like the transition matrix for the Markov chains, yes? They are the
Irregular, so adjacency
Irregular.
matrix and Markov chain
So-
matrix is the same.
Can you say something on that on the Markov chain? What kind of, if it's translated into Markov
If you
chain,
have a
what kind
large
of
curve,
birthday
you
we are
have a fast mixing.
Huh?
Small second eigenvalue means fast mixing to the stationary distribution.
Oh, okay.
Yeah, no, I think what you just said is a good ways to illustrate it. So when the girth, how to say that? So I guess when the second eigenvalue is small, it roughly means that your deregular graph looks like trees in local neighborhood.
Okay.
So the girth will be small. So there are no short cycles. So the girth is small, there are no short cycles.
Girth is large, right?
Oh,
Girth
sorry,
is the length of
sorry, girth is
cycle.
large. So sorry, girth is large, there are no short cycles. And in terms of Markov chains, it should represent that when you do a random walk, start from your vertex, it's unlikely that you return. So meaning that the mixing time is fast. I guess that's roughly a bunch of ideas that are correlated to each other.
How about the random matrix? Any
The-
connection to the random
the-
matrix?
Okay, so
Yeah, so the
this-
contraction of F requires this randomness.
yeah, so okay, so this statement, so Friedman's theorem says that when H is a random deregular graph, the second eigenvalue is asymptotically this, at most this. And we know that this is the best we can do because we also know from Alon that this is true. Right. This is like we discussed this at the earliest of today. So this is true. And so Alon tells us like second eigenvalue is at least as this. But then Friedman's theorem says that when H is random, second eigenvalue is also asymptotic at most. So meaning that random deregular graphs should mix very fast.
What's the definition of random deregular?
Yes, when H is a random deregular graph.
What's the precise?
You can take it uniformly at random for a fixed n.
Oh, okay.
There are only finite many such
vertices.
graphs you can take.
So uniformly random.
Okay, thank you.
Okay, thank you.
Thanks for coming.